Hello, can you hear me? Okay, I'll just wait for 2 minutes and I'll see if other participants are going to join and then I will start the session. Okay, I'll get started with the today's problem solving session. Let me share my screen. So, good evening, everyone. I hope you're able to hear me. Can one of you unmute and let me know if you're able to hear me? Okay, thank you. So, I'm Lokeshwari. I'm a PhD scholar. So, last class we had first problem solving session, and this is the second one. So, this will be related to mostly to the second week's lecture content. In the second week's lecture content, there is like lot of derivations and everything. So, in between, there will be certain derivations, important things which were not derived. So, small portions of the derivations also we'll see how to derive, and any other doubts if you have, those things also we will discuss. So in the previous problem solving session there were a few doubts that were asked. So one was like, is there any proof for D'Alembert's principle? Actually there is a proof for D'Alembert's principle. It is just a restatement of Newton's second law of motion, and it's actually proved using a virtual uh, displacement method. It's actually a very old derivation. Probably it was proved in 18th century or something. So I think it's not very important to know that derivation. And the second question is, how is the natural frequency of a system is square root of k by m. So that is okay. The second question is like, how is natural frequency is equal to square root of k by m. This can be understood from the the way we obtain the solution for the free undamped vibration. While deriving that equation, we can understand this. So, what is the equation of motion for the undamped free vibration? It is mx double dot plus kx is equal to 0. So, this can be rewritten as x double dot plus k by m x is equal to 0. Let us not assume that omega n is equal to k by m. Let us just solve this equation. So if we solve this equation, again we'll have the solution as usual. We're going to have a cos k by mt plus b sine k by m times t. We are not substituting that omega is equal to k root k by m. Otherwise everything is same. Now if we see that this again can be written in a different form, right? So if you see this equation, we have the cos term as well as the sine term. What is the period for these two things? Period is 2 pi. What is meant by period? So after, uh, so if we do the theta plus 2 pi, if we substitute that angle in the cosine term or sine term, we are going to get the same value. That is what period means. So the period is 2 pi. So that means cos of k by m t plus 2 pi, and we can do the same for sine of k by m t plus 2 pi. So after an angle of 2 pi, we are going to get the same displacement. That is what this period means, right? But we want to express this in terms of time. So for that, what we do, we just take out k by m common. T plus 2 pi by k by m. So I think we are going to have here square root, right? Because we will have lambda square plus k by m is equal to 0. Lambda is equal to plus or minus I square root of k by m. So here we have square root of k by m. So we are just taking out square root of k by m as common. So that means after a time period of 2 pi by square root of k by m, we are going to get the same displacement. That means the time period for this motion is 2 pi by square root of k by m. So since this is just dependent on the natural properties of the system, this is called as natural time period. So without making any assumption, this is how we will get. Since we know the time period, what will be the frequency? Frequency is nothing but 1 by Tn. That is the cyclic frequency. 1 by Tn will be square root of k by m divided by 2 pi. This is the cycles per second or hertz. And one cycle, we just want to convert this into radians per second to get the angular frequency. So that we can simply do by converting these cycles into radians. One cycle is equal to 2 pi radians, right? So we'll have the angular frequency as square root of k by m divided by 2 pi multiplied by 2 pi. So this way we have the frequency, the angular frequency as root k by m. And this is called as natural frequency because it's again just like time period, it's only dependent upon the properties of the system. So this way we can understand how the natural frequency is square root of k by m. I hope this clears the previous doubt.
Why did we multiply 2 pi to frequency?
So this is the cyclic frequency. That means this is the time required for one complete cycle. So one cycle is 2 pi radians, right?
2 pi.
Yeah.
Yes.
So
Okay.
to get in radians per second, we just multiply.
Got it.
Okay. So are there any other doubts like related to lecture or anything else? Okay, if there are no other doubts, then we'll move on to the week two's contents. This is mostly derivation, so and also there is lot of concept to understand. So I thought I will cover some of the concept. After that, we will solve few problems. Related to this concept, I will try to cover most of the problems in the next week, because in the if you see the week 3 contents also, most of the problems related to this thing are covered in the week 3 videos. Okay.
Ma'am, could you see D'Alembert's principal derivation? Or
Yeah, actually, so there is a proof. It's actually a restatement of the Newton's second law of motion, and it's a very old proof based on principle of virtual work. So that could be found. It was actually derived in 17th century or something. It would be a very long derivation.
okay, ma'am.
Yeah. So I think, and also it's the original will be in French, so it's difficult to understand and derive in this problem solving session.
Okay.
So, okay, now we'll see the response for the undamped forced vibration. So, till now we have been seeing the free vibration of single degree of freedom system without any external force. So, in this week, this is completely about the forced vibration when the single degree of freedom is subjected to harmonic force, and we will be using this sinusoidal harmonic force P naught sine omega t for the discussion. So, so this is a single degree of freedom system that we are considering. And there is an external force P naught sine omega t. So this force is varying with an angular frequency of omega, and this omega is also called as forcing frequency. Now, if we draw the free body diagram of this to obtain the governing differential equation, so we are going to have kx in the direction opposite to the displacement direction, and cx dot. Okay. Now let's focus only on undamped vibrations. So there won't be this component. So initially, for simplicity, we will just solve this undamped forced vibration. Now the another force is P naught sine omega t. So if we write the equation of motion, we will have, and this is the positive direction for the displacement. Then we will have P naught sine omega t minus kx. This unbalanced force will be equal to the inertia force as per Newton's second law of motion. So we'll get mx double dot. So this is the governing equation for this system. And here this is not a homogeneous differential equation, but this is a non-homogeneous equation. So that means we are going to have the solution as a sum of a complementary function plus the particular integral. This we learn from basic course on this uh, differential equations, how to solve and all. So from that we learn this. So for this, u of t is equal to, sorry, let me follow it consistently. Okay, let's follow this as u of t. U of t is equal to uc of t plus up of t. So as a trial function, when there is a sine term, sine or cosine term, we can take up of t as c sine omega t and solve for this constant c. If we solve for this constant c by substituting for up double dot of t and up of t in this equation, we will obtain up of t as this component. So I hope this much is understood from the lectures. Okay.
What is UP of T?
This is the particular integral that is correspond to the this forcing. forcing function.
Okay. The component of general solution.
No, it's not a general solution, it's particular integral. So this
Okay.
whole thing is a general solution actually for this non-homogeneous equation. So when we don't have anything on the right hand side, then only this complementary function that is called as a general solution. General solution means we don't have any of the, we have not imposed the initial conditions or boundary conditions yet. That is called as a general solution. And when we impose the initial conditions, we get the particular solution for that inputs or initial conditions, sorry. So, and uh, so this is summation of UC, right? UC means the complementary function. The complementary function is obtained by setting this equal to 0. So that we have already seen for the free vibration in the previous session. So the whole equation would be u of t is equal to a cos omega nt plus b sin omega nt plus this particular integral which we have obtained. So how do we obtain this a and b? By using the initial conditions again, which are like the initial displacement and the initial velocity. So if we solve that, we will get this complete solution equation. So if we see this, there are terms which can be differentiated using the frequency with which the components are varying. One is this these two terms which vary with the natural frequency, and this term which is varying with the forcing frequency omega. So this portion is classified as transient response, and this thing is called as steady state response. So why this name is derived? Because when damping is present, this transient response dies out after certain number of cycles. However, this steady state response remains. So total response or the total displacement is just the summation of these things. So this is the total response. So this graph is plotted for omega by omega n ratio is 0.2, and initial displacement is 0.5 times this P naught by K, which is nothing but the deformation caused by the force amplitude P naught without considering any variation. So the initial velocity as omega n P naught by K. These are the conditions for which this graph is plotted. So you may ask that is it possible to obtain a simplified expression where we can obtain the amplitude for the displacement. So that is very difficult because we have different natural frequency and the forcing frequency. So we can't actually obtain a simplified equation. So that's why it's shown as plot here. So, and again, this solution is valid only for when omega is not is equal to omega n, because when omega is equal to omega n, this term becomes undefined. So as I said before, this transient response dies down after certain time, and hence whenever we study the forced vibrations, we examine the steady state response. So if we consider this steady state response, this is normally written as P naught by K times Rd multiplied by sine omega t minus phi. I'll explain what these things are. So here Rd is called as deformation response factor. And and phi is when omega by omega n is less than 1, phi is equal to 0 degrees, and omega by omega n is greater than 1, then phi is equal to 180 degrees. So we can plot this RD as a function of omega by omega n. Why? Because this is completely dependent upon this ratio. Hence, it is plotted for different ratios of omega by omega n as shown in this plot. So you can observe few things that when omega by omega n is very small, then this RD value will be close to 1. And when omega by omega n is close to, when it is 0, then RD value will be close to 1. What does it mean? It means that the displacement amplitude at steady state for this will be close to the static displacement, that is P naught by K value. Otherwise, when the frequency ratio is much higher than 1, then it is like it approaches 0. That means that the force is varying very rapidly, and then but the single degree of freedom mass, that won't be moving because of this rapidly varying force. That's what it means. And when omega by omega n is close to 1, then it's going to have very high value. So this is another plot which just shows how the phase angle varies with respect to the frequency ratio. So it has some physical significance. So when omega by omega n is less than 1, the force and the direction of the displacement will be in the same direction. So if the force is acting towards the right, the body also will be displacing towards the right. Otherwise, if the body is uh, so when the phase angle is 180 degrees, if you are applying force towards the right, the body will displace towards the left. That's what it means. So this is what happens when omega is not equal to omega n. When omega is equal to omega n, that solution whichever we have seen before is not valid anymore, because the forcing frequency is same as the natural frequency, and for this case the particular integral will be having the it should have t in the product. So we assume that the particular integral will be in the form ct cos omega nt. If you take ct sin omega nt, you will find that the coefficients for this will be equal to 0. That's why we can just take ct cos omega nt and then find out the constants. So if you do the same thing for this cos omega nt, okay, let's just do this. Xp double dot t, xp dot t, xp dot t will be uh, c cos omega nt minus so, and xp double dot t will be equal to minus c omega n sin omega nt minus ct omega n square cos omega nt minus c omega n sin omega nt. So if we substitute this and this in this equation, we will have, so here we have minus 2c omega n sin omega nt minus ct omega n square cos omega nt plus ct omega n square cos omega nt. This is equal to p naught sin omega nt. So these two terms get cancelled. So we will have c is equal to, just by comparing the coefficients of sin omega nt, we will have c is equal to minus p naught by 2 omega n. So here there will be m in the denominator because the whole equation will be dividing by m. So here we have m. So this is what we will get. And let's substitute this in the equation. So m can be written as omega n square is equal to k by m, which means m is equal to k by omega n square. And this coefficient can be written as 2k omega n will come up. So this is the particular integral for the case of resonance condition. So the total solution will be a cos omega nt plus b sin omega nt minus p naught by 2k omega n. So this is the particular integral with which we have assumed, and I'm just substituting the value of c. So it will be minus p naught omega n by 2k t cos omega nt. And we can just see the equation for 0 initial conditions, that is u of 0 equal to u dot of 0 is equal to 0. For this thing we can simplify. We can find out the a and b constants. So x of t will be equal to a minus, so this term also will be 0. So that means a is equal to 0. And velocity will be minus a omega n sin omega nt plus b omega n cos omega nt minus p naught omega n by 2k cos omega nt plus p naught omega n square by 2k t sin omega nt. So at 0, this will be, this term is gone, and also this term is gone. We just have b omega n minus p naught omega n by 2k. That means b is equal to p naught by 2k. So the total equation can be written as x of t is equal to p naught by 2k sin omega nt and then minus P naught by 2k omega nt cos omega nt. So from this equation, we can find out the local maxima which give the amplitude at each cycle. So if we do that, okay, let me write down in the next page. So we can take P naught by 2k as common, and we will have minus omega nt cos omega nt. So dx by dt to find out the local maxima and local minima. Minus omega n cos omega nt, and then we have minus omega n square t sin omega nt. So this must be equal to 0 at local maxima or minima, and this thing gets cancelled. So t is not equal to 0, that means sin omega nt must be equal to 0. We can write, that means omega nt must be equal to integral multiples of uh, pi, j times pi, where j is equal to 1, 2, 3, and so on. So at these values, we have local minima. And if you see further, then we'll see that at odd multiples of pi, we will have local maximas. So if we substitute 1 for j, then x of t is equal to p naught by 2k. That means t is equal to pi by omega n when j is equal to 1. So let's substitute this p naught by 2k, and this term will be 0 because it will be sin pi is 0, and then here we have minus omega n times pi by omega n, and cos pi. Cos pi is minus 1. So here we have x of t is equal to p naught by 2k multiplied by pi. And if we substitute 3 pi, then x of t will be p naught by 2k times 3 pi. So this is at j is equal to 3. That means t will be 3 pi by omega n. If we convert this into the time periods, then we'll have 3 pi by 2 pi by td. That means 3 by 2 times td, and this will be 1 by 2 times td. At half of the cycle, there is one local maximum, and in the next cycle, in that half, there is one more local maximum. So the difference between these two amplitudes gives how much amplitude is increasing for this resonance condition. So that is P naught by 2k 3 pi minus this value, which is just pi. So here we have P naught by k times pi. So that means every time the amplitude increases by P naught by k times pi. So that means with time it keeps on increasing, and this is an unbounded value. But however, this is a pretty ideal condition. Normally, all the structures actually have damping, and because of the damping, this response becomes bounded, which we will see in the next sections. So, are there any doubts in this thing? So, if
Ma'am,
there are,
what is
yeah,
ma'am, what is UST naught?
so UST naught is just the displacement value that will happen for that system when this amplitude P naught is applied. That will be just force divided by the stiffness of the system, that is P naught by K. UST naught is equal to P naught by K. This is the deformation in the body when we apply this
So
amplitude
why
P
we
naught.
are taking relative measurement of displacement with respect to this UST naught in the
Because,
graphs?
okay, graphs. Because if we take the ratio, then we'll get some numerical values and it can be plotted. Otherwise, there will be some variables.
Okay. Okay.
Yeah. Okay. If there are no other doubts, then we'll solve this one simple problem. So, the mass m, stiffness k, and natural frequency omega n of an undamped SDF system are unknown. These properties are to be determined by harmonic excitation tests. At an excitation frequency of 4 Hz, the response tends to increase without bound. So that means when an excitation frequency of 4 Hz is applied, the response is increasing without bound, means it's the resonance frequency. That means the excitation frequency will be equal to omega n. Next, a weight W is equal to 5 pounds is attached to the mass m, and the resonance test is repeated. This is the first case. So omega n is equal to 4 Hz. Let's call this as omega n 1 for the first case. The second case is 4 Hz, means this is cycles per second. So this must be converted into radians per second because omega n is angular frequency. So this will be equal to 4 multiplied by 2 pi radians per second. So after attaching a mass of, this has a weight of 5 pounds. So here the units for weight is pounds, and for mass it will be 5 pounds second square per inch. Sorry, these are just the units. Mass will be weight by g. So for the second case, we have omega n 2 is equal to 3 cycles per second. Because when a mass m is attached, resonance occurred at 3 Hz. That means the natural frequency of the system when a mass is attached has changed to or reduced to 3 Hz. So this is equal to 4 multiplied by 2 pi radians per second. Now we will just substitute for omega n. Omega n1 will be square root of k by m. M1 we can call it as is equal to 8 pi. And root of k by m1 plus m2 will be 6 pi. Now we can take the ratio of this. We can square on both sides. Then we will have k by m1 is equal to 64 pi square. K by m1 plus m2 is equal to 36 pi square. Now if we take the ratio of these two equations, we'll have m1 plus m2 by m1 is equal to 64 by 36. So we can find out the relation between m1 and m2. Four 16s are and 4 9s are. Then we will have 7 m1 is equal to 9 m2. That means m1 is equal to 9 by 7 times. M2 is 5 by g, which is 5 by 386. So we'll have 0.0166 pound second square per inch. Now they're asking us to also find the stiffness of the system. For that we can just substitute in one of the equations. So K will be equal to 64 pi square multiplied by mass 0.0166. If you evaluate, you would get 10.48 pounds per inch. How much you're getting this value? Yeah, we would get 10.48. Okay, this is a simple problem. We will go to the next concept, which is damped forced vibrations. So similar to what we wrote the equation of motion, we can write the equation of motion as follows for the damped forced vibration. This left part of this equation is very similar to the free vibration, free damped vibration. Additionally, we have the forcing term on the right hand side. So again, similar to what we have done, here also there is going to be complementary function in the particular integral. So this is already derived in the class. So the whole equation for this will be a cos omega dt plus b sin omega dt plus we have 1 minus omega by omega in the whole square sine omega t plus 2 zeta omega by omega in the whole square cos omega t. So these two coefficients again have to be evaluated for particular initial conditions. This is the whole solution for this damped forced vibration. So again this component is called as transient response and this is called as steady state response. So if you plot this again equation, you can see that this is the total response and this is the steady state response. So after certain time, the total response can be pretty much approximated just as this steady state response. So that is why whenever we are talking about response factors, we always consider only the steady state response and take the ratio with respect to this static displacement. So let us just consider only this component. So then after some time, this will just be minus, here we have P naught by K. Omega n square, the whole square, sine omega t plus 2 zeta, omega n by omega n, omega by omega n the whole square, cos omega t. So now, similar to what we have written for the free vibration response, by assuming that cos omega t is equal to this term, let's call this as C and this as D. C divided by square root of C square plus D square, and sine omega t is equal to minus D by square root of C square plus D square. So if we make this assumption, then it can be simplified. This x of t can be simplified as square root of C square plus D square uh, sine of omega t minus phi. So where phi is equal to tan inverse of minus d by c. Hence the whole equation will be completely x of t is equal to p naught by k multiplied by 1 by square root of 1 minus omega by omega in the whole square plus 2 zeta omega by omega in the whole square multiplied by sine omega t minus phi. So this is the dynamic response, and if we take the if we take the ratio of this with respect to p naught by k, this will be 1 by square root of 1 minus omega by omega in the whole square plus 2 zeta omega by omega in the whole square, this sine term minus p, and this term is called as deformation response factor in the case of damped forced vibrations. This Rd is equal to 1 by square root of 1 minus omega by omega in the whole square plus 2 zeta omega by omega in the whole square. This is the deformation response factor for this damped forced vibrations. Similar to this deformation response factors, we also have the velocity response factor and the acceleration response factors. So we have x of t p naught by k rd sine of omega t minus phi. So by differentiating this ones, we will get the velocity. We have p naught by k omega cos of omega t minus phi, and we can divide on both sides with omega n. So we'll get omega n times p naught by k is equal to rd omega by omega n cos of omega t minus phi. So that means this term is called as velocity response factor. This is the ratio of, if you see, this is the static displacement multiplied by the natural frequency. And the ratio of the dynamic displacement, dynamic velocity to this value is called as dynamic response velocity response factor, RV. So RV is equal to RD omega by omega n. So if we divide this once again, we will get the velocity response factor as RA is equal to minus omega by omega n the whole square times RD. And here the ratio is the acceleration, the dynamic acceleration to the this thing because of the static force. This is called as acceleration response factor. So this is what I have explained so far, and we can see how this, if you notice this thing, the deformation response factor, it is dependent on the two factors. One is the damping ratio, and then the other is the forcing the frequency ratio. So normally you would have seen plots for various damping ratios and the frequency ratios. So it will be something like this. So this is 1, the frequency ratio of 1, and this is the displacement response factor or the deformation response factor. So if we see when the frequency ratio is close to 0, then this value RD will be very close to 1. That means the dynamic displacement will also be close to the static displacement P naught by K. But when it is very high, then this response factor will approach 0. And one more thing to note is this peak value is not occurring at omega is equal to omega n, but at a slightly smaller value. So we'll see why that is. So, and for RV, and this is for certain damping ratio. If the damping ratio is reducing again, it will be something like this. That means when the frequency ratio is around 1, then this damping ratio will have some influence in the deformation response factor. Otherwise, when it is outside this limit, either it will approach 1 or it will approach 0. So similar plots can be drawn for RV and RD, RV and RA. So for these cases, we will have something like this. So for this, when the ratio is very small, it approaches 0. And when the ratio is very large, then it approaches certain small value. And when it is close to 1, it's very high. For this velocity response, at omega is equal to omega n, we obtain the maximum peak value. So for acceleration, it will be so for this also the peak does not occur at omega is equal to omega n, but at somewhat smaller value. So we know the response factors for velocity, deformation, and acceleration. So in these plots, these points correspond to the global maxima of those response factors. So those things we can obtain by differentiating with respect to the frequency ratio. So for example, we'll solve this for deformation response. So RD is equal to 1 by square root of 1 minus omega by omega in the whole square plus 2 zeta omega by omega in the whole square. So for this thing we can find out at what frequency the maximum value is occurring. So at whatever frequencies the maximum value occurs, those frequencies are called as resonance frequencies in the case of damped forced vibrations. So we can just for simplifying this equation, we can make a substitution that uh, some some a is equal to omega by omega n. Then we have to differentiate this with respect to a. Then it will be minus 1 by 2 1 minus a square the whole square plus 2 zeta a the whole square, this whole power minus 3 by 2. And this whole term should also be differentiated with respect to a. So then we will get 2 of 1 minus a square multiplied by minus 2a plus 2 times 2 zeta a multiplied by 2 zeta. So for maximum value, this will be equal to 0. So we will have only this numerator we can consider. And we can, so this thing will remain minus a plus 2 zeta square a. This is equal to 0. Now we have minus a plus a cube plus 2 zeta square a is equal to 0. So we have minus 1 plus a square plus 2 zeta square. That means a is equal to square root of 1 minus 2 zeta square. So we are considering only the positive value because this ratio will always be positive. So that means omega by omega n is equal to square root of 1 minus 2 zeta square. This will be the maximum because from these plots we can say that this plot only has one global maximum and no local minimas. So at omega is equal to omega n square root of 1 minus 2 zeta square, there will be a maximum response for RD. So this value will be slightly smaller than omega n. That's why we observe that this maximum is occurring at a value which is slightly left to this omega is equal to omega n. Are there any doubts in this or anything else? So if there are no doubts, then we'll solve one problem. So an SDF system is excited by a sinusoidal force. At resonance, the amplitude of displacement was measured to be 2 inches. And also once we substitute this maximum frequency ratios in these response factors, then we will have the maximum um response values for each of the variables, that is deformation velocity and acceleration, as like this. So for deformation, the maximum value is 1 by 2 zeta square root of 1 minus zeta square, and for velocity it is 1 by 2 zeta, and for acceleration it is 1 by 2 zeta square root of 1 minus zeta square. So at resonance, the amplitude was measured to be 2 inches. So whenever they're talking about amplitude of displacement, they always mean the amplitude of the steady state response. At an exciting frequency of 1/10 the natural frequency of the system, the displacement amplitude was measured to be 0.2 inches. Estimate the damping ratio of the system. So at different forcing frequencies, they have given the amplitudes of that particular system, and they want us to estimate the damping ratio. So for this, we can directly use the deformation response factors that we know. So first of all, at resonance, we can assume that the damping ratio is very much less than 1. And if we assume this, then the amplitude at resonance is this. So this will become 1 by 2 zeta, because zeta is, this term will be close to 1. So this is the response factor. That means the actual displacement will be 1 by 2 zeta p naught by k. And at an exciting frequency of 1/10 of the natural frequency. So omega is equal to 1 by 10th of omega n, which means omega by omega n will be 1 by 10. The displacement amplitude was measured to be 0.2 inches. So for this, 0.2 inches, this is given as 2 inches. So for any other ratio, we know that this amplitude will be p naught by k multiplied by 1 by square root of 1 minus omega by omega n the whole square plus 2 zeta omega by omega n the whole square. So this is equal to 0.2. Okay, in this we can substitute for omega by omega n and then simplify. So what will be p naught by k 1 by square root of 1 minus 0.01 the whole square, because 1 by 10 the whole square is 0.01 plus 2 zeta, or else zero point 0.2 times zeta the whole square. So P naught by K 1 by square root of this will come out as 0.9801 plus 0.04 zeta square is equal to 0.2. So we can take the ratio of these two amplitudes at different frequencies to eliminate this P naught by K term. 1 by 2 zeta divided by 1 by square root of 0.9801 plus 0.04 zeta square is equal to 10. So can you people solve this and then tell me what value of zeta you're getting? Are you trying this? Are you able to solve this?
uh, 0.049.
Yes, yes, correct. So we would get a zeta of 0.049. So this problem can be directly solved by approximating that when the damping ratio is very small, when the frequency ratio is very small, we can approximate the displacement as P naught by K, because this dynamic response factor will be close to 1, as we have seen in this plot. So when we do such approximation, we would get a value of zeta is equal to 0.05, which is very close to what we have got now. So till this concept, I will just summarize the main points that we have seen. So whenever we are considering the this response factors, we will directly consider only the steady state response, and then we will take the ratio with respect to this static response. So these things are useful for obtaining the properties of a system when we do uh, some tests using this harmonic generator test platforms. So our goal is like to understand how much is the response when that structure is getting subjected to the dynamic forces. So that is what we have seen till now. And another thing to understand is so This response factors are dependent on both frequency ratio as well as the damping ratios. So whenever the damping is very small, the response factor will become very high. Okay. Are there any particular doubts related to this problem or like any other concepts? Okay, if there are no other doubts, then we will move on to the concept of this half power bandwidth. This concept is also useful for determining the damping ratio and the properties uh, by measuring the response of the system at various frequency ratios. So what is this half power bandwidth basically? So we have this deformation response plot for various frequency ratios. So have you people gone through the example problems that were explained during week 2 content? Oh, okay. So this is the deformation response factor and the frequency ratio. For a particular damping ratio, we have something like this. So this is the amplitude at the resonance. And at certain frequencies, so there can be two frequencies for which the amplitude is same on either sides of this resonance frequency ratio. So let's call these ratios as omega A and omega B. So it would be omega n, omega n. So this concept says that we have this relation omega b minus omega a by omega n is equal to 2 zeta when this amplitude is equal to 1 by root 2 times of this resonance amplitude. So these frequencies are such that they have the amplitudes as 1 by root 2 times the resonance amplitude. This can be proven actually by for that we have to find out the frequencies for which the amplitude is equal to 1 by square root 2 times the resonance amplitude. So let's do that. So we will begin with the deformation response factor for the general equation which we have. So 1 minus omega by omega in the whole square plus 2 zeta omega by omega in the whole square. So this is the amplitude at any arbitrary frequency ratio. So we want to find out this frequency ratio such that this amplitude is equal to 1 by root 2 times the resonance amplitude. So we have seen just before the resonance amplitude is 1 by 2 zeta square root of 1 minus zeta square. Okay. Now we can just do the inversion and then squaring on both sides. Then we will get omega n the whole square. Uh, Please try to derive this along with me. Plus 2 zeta omega by omega n the whole square is equal to 2 4 zeta square 1 minus zeta square. So let's further expand this. Plus 4 zeta square omega by omega n the whole square. Eight zeta square of 1 minus zeta square. So we can bring out all the terms to one side. So omega by omega n whole power 4. We have 4 zeta square minus 2 times omega by omega n the whole square plus 1 minus 8 zeta square 1 minus zeta square is equal to 0. So we can find out omega by the roots for this equation. So assuming that omega by omega in the whole square is x, using the standard formula, then we will get zeta square plus or minus 2 zeta 1 minus zeta square. So we have got two roots. So these two roots must correspond to these two frequency ratios. And also for smaller damping ratios, zeta much lesser than 1, we have omega by omega n the whole square can be approximated as 1 minus 2 zeta square. Because this value multiplied by this again, another value would be very small. So omega by omega n will be approximately equal to 1 plus or minus 2 zeta. So then we have omega by omega n is equal to 1 plus 2 zeta, and omega a by omega n will be equal to 1 minus 2 zeta. So if we just subtract these two values, omega b minus omega a by omega n, now we'll have 2 zeta. So this is the relation. So this can be used to find out the damping ratio of a structure. Just like how we use the method of this logarithmic decrement when there are no forcing component present.
So these are the standard result.
Sorry? These are the
these are the standard result, no?
yes, yes,
Which we need to memorize.
yes, yes.
Okay.
Because we can't derive these things every time. Yeah, like you said, we have to memorize some of these things. The
Right.
deformation response factors, the velocity response factors, and the resonance frequencies at which these things occur.
Yes.
So these are some of the important things which we have to remember.
Okay.
So we'll solve one problem. So a spring mass system is suspended from the ceiling of an elevator. At time t is equal to 0, the elevator starts from rest with an acceleration g in the y direction, where g is the acceleration due to gravity. The acceleration of the elevator remains constant. At time t is equal to 0, the mass is displaced at a distance delta in the y direction from its equilibrium position and go. So there is a spring mass system and there is no damper for this. This is suspended from the ceiling in an elevator, and then at time t is equal to 0, two things are happening. One is the mass is being displaced by a value delta, and also this elevator begins to accelerate in the uh, upward direction. They said y direction, which is this upward direction. The acceleration of the elevator remains constant. So all these things is given. Now we have to derive few things for this case. So one is develop the equation of equilibrium of the mass m. So for this mass m, we have to write down the equation of equilibrium. So I think they meant dynamic equation of equilibrium. So let's do that. So let's write down the initial conditions they have given for this mass, which is uh, they have said that x of 0 is equal to delta. So this x of 0 is with respect to y of 0 is equal to delta. So in this direction, they have given a displacement because this is the positive direction they have given. And this displacement is with respect to the support to which the spring is attached. And also, uh, let's draw the free body diagram of this mass. We have this mass m. On this thing, there is only one force which will be acting in the downward direction, which is k y, which is ky, because we have pushed it upwards, so it will be acting downwards. And also there is, so this unbalanced force, this must be equal to the acceleration of this body. And this acceleration must be with respect to some inertial frame of reference, like which is not moving. So we must take this reference which is not moving. So that would be the total acceleration. And this total displacement would be the displacement of the elevator with respect to the ground, which we can write as ye plus and also the displacement of this mass with respect to the elevator, which is small y. So that means the total acceleration will be ye double dot plus y double dot. So we know that the acceleration of the elevator, so the acceleration of the elevator is g in the upwards. So it is, we can write y double dot is equal to g plus small y double dot. So this small y double dot is the displacement of the mass with respect to this frame which is attached to this elevator. So now let's substitute everything in this equation. So now we have minus k times okay m g plus y double dot plus ky is equal to 0. That means my double dot plus ky is equal to minus mg. This is the equation of motion. This is the first part. The second part is derive the expression for the displacement of the mass as recorded by an observer standing in the elevator. So this is the displacement of the mass with respect to the elevator. So this is the equation which we already have. We just have to solve for this displacement. So we can simplify this part B. So y double dot plus k by m y is equal to minus g. So if we solve, we would get this is similar to the equation which we have been solving till now. So we will get a cos omega nt plus b sin omega nt minus g by omega n square, which is this. Now we can substitute the initial conditions for finding out this constants. And also y dot of 0 is equal to 0 because there was no velocity at time t is equal to 0. So delta is equal to a minus g by omega n square, which means a is equal to delta plus g by omega n square. So that means we have the displacement equation as, and also if we again do the derivation for finding out d, y dot of y dot of t is equal to minus a omega n sin omega nt plus b omega n cos omega nt. Here we'll get b as 0. So we just have the displacement of the mass m in this frame of reference, yx frame of reference. We are going to get y of t is equal to delta plus g by omega n square cos omega nt minus g by omega n square. This is for part B. I hope you are able to follow. Are there any doubts like in the derivation of this equation of motion? Okay, I don't know like whether you're able to follow this or like should I explain it once again? Okay, let me continue this problem. Then the last component is determine the total displacement of the mass recorded by an observer standing on the ground in the xy coordinate system. So now we need to find the total displacement, which is the elevator displacement y is equal to elevator displacement plus this component which we have obtained now. So this is starting from rest from 0 value, and then it is accelerating with an acceleration g. So for this we can use the kinematics equation. So what is this kinematics equation? We know from basic kinematics that displacement is equal to u naught t plus half at square. In this, u naught is 0, the initial velocity is 0, and the acceleration is given as g. So the displacement of this elevator at any time t with respect to the ground would be equal to half gt square. Hence, the total displacement of the mass with respect to an observer on the ground would be y is equal to delta plus g by omega n square cos omega nt minus g by omega n square plus half gt square. So this is the total displacement. Okay. Any doubts till here? If there are no doubts, then we can solve some more problems. We can. Okay. Let's solve one more problem. So the question is like, in a forced vibration test, under harmonic excitation, it was noted the amplitude of motion at resonance was exactly 4 times the amplitude at an excitation frequency 20 percentage higher than the resonant frequency. So we need to find the damping ratio zeta for this system. So they have conducted some forced vibration test using the harmonic excitation. For different frequency ratios, they have given the amplitude response and the relation. So we need to find the damping ratio. How would you solve this problem? Please try it out on your own. You can assume that the damping ratio is very smaller than 1 and can make appropriate approximations in the amplitudes, in the amplitude equations. So I will start this problem. Are you trying?
So that means in case of theta less than 1,
Yeah.
we can say that resonant frequency is same as natural frequency.
Yes, it would be very close.
Okay. Can we attempt this question this way? Or,
Yeah. Yep. Please go ahead. So we can assume that the resonance frequency is equal to omega n. This is the first frequency. The other thing is at a frequency 20 percentage higher this, so 1.2 times omega n. So the ratio of these amplitudes they have given us 4 at these two frequencies. So at resonance frequency it is 1 by 2 zeta, 1 by square root of 1 minus zeta square. So again this can be approximated as 1 by 2 zeta times UST naught. And the general equation is 2 zeta omega by omega in the whole square. Now with this approximations, please try to solve the problem. Okay, let me also solve the problem along with you. So now we can substitute for omega by omega n in this second equation. So we will have 1 by square root of 1 minus 1.2 whole square plus 2 zeta 1.2 the whole square. times est naught. So we can simplify this. Square root of 0.1936 plus 5.76 zeta square. So again, we can take the ratio of the two. So 1 by 2 zeta 5.76 zeta square. This is equal to 4. So we can do squaring on both sides. 5.76 zeta square 4 zeta square is equal to 16. Point 1936. How much is the zeta square you got?
So 0.057.
Yes. 0.057. So these are like very simple problems that are related to this concept. There are also other problems that we will solve in the next class. I thought I will take up the concept this week because there is like so much concept involved in this week 2's videos. And also in the week 2 videos, there are some problems that are solved. Uh, both of you have not gone through the videos.
I have not gone through.
Okay. I thought maybe if you had some doubts, we can take those questions also. But we can see some examples. So one of the example is writing the equation of motion. Then there is a ground displacement. So there is a mass and there is a ground motion with acceleration xg double dot. The subscript g indicates the this displacement is of the ground, and we have a certain frame of reference away from this ground. So the total displacement of this mass we can take as xt. Now for this, when there is a ground motion, we want to find out the equation of motion for this particular case. So when there is a ground motion, let's say that the ground is displaced by an amount xt, then it would be xt, and then there is also deformation here. So this deformation would be with respect to this ground. Let's call this as x. So the total displacement is x plus xt. This is with respect to the ground. Sorry, the displacement of the ground with respect to this frame of reference, this so-called inertial frame of reference. Now we can draw the free body diagram for this mass. So there is going to be a spring force kx. Here we have to consider x because this component, this stiffness resistance comes only because of the deformation in this element. So deformation is nothing but the relative displacement, and this rigid body component xg. So this rigid body component corresponds to the displacement of both of these things. Hence, this will not create any resistance in this spring. Okay, and also we have acceleration, the total acceleration mxt double dot, and so xt double dot would be x double dot plus xt double dot, which is the ground acceleration. We have to consider the total acceleration of this mass with respect to some frame. So we can write down plus kx is equal to 0. So if we again do the substitution, we will get minus mxt double dot. So this is the equation of motion for this condition. And there is another example of a disc attached to a rod, and then a rotational displacement is applied for this. And for this case, we need to write down the equation of motion. This is another example that's already solved in the videos. So there is a rod of diameter d, which is fixed. And this disc has a mass of m, and then an angular displacement theta is given, and then it is left. So and let us assume that the shear modulus for the rod is g, and it's also assumed that this is massless. So from this strength of material course, we learned that for this for circular rods we have this stiffness k is equal to gj by l, or the torsion that is generated because of angular deformation theta is equal to the torque. So let's say that we are giving an initial rotation of theta in this direction. There will be a counter torque that will be applied on this mass that is generated from this rod. So this torque will be equal to gj theta by L, where J is the moment of inertia for this rod. So analogous to the force, here we have the here we have rate of change of angular momentum because we have the angular displacement. So angular momentum is nothing but I omega, and then if we do the rate of change of angular momentum, we would get the force which is I theta double dot, which is the inertial force in this case. So we have I theta double dot plus gj theta by L is equal to 0. Now, this is the mass moment of inertia that we have to consider. So for this case, mass moment of inertia is mr square by 2. So we have mr square by 2 theta double dot plus g, and the moment of inertia for rod of diameter d is pi d power 4 by 32. L theta is equal to 0. This is the equation of motion for this. So these are some of the examples. Actually, all the examples are explained in detail in the video. So I request you to go through the videos. And if you have any doubts, like we can take it up in the next class. So are there any doubts? Any other doubts related to anything like assignments or like anything else? Okay, next class we will solve like mostly problems. If there are no doubts, then we can close the today's session.
Okay, ma'am.
Okay. Thank you.